Hello everyone, let's take a look at our next problem. This is another problem submitted by a viewer. It says let Pn be equal to 1 plus x plus 2x squared plus 3x cubed plus 5x to the 4 and so on, where, okay, so we have an nth degree polynomial where the coefficients are the terms in the Fibonacci sequence. And it says, for which n does p of n equal 0 have an integer solution? Interesting. Okay, so let me write out what the polynomial is exactly. Okay, so I've written out all the information given here. You have to be a little bit careful, I suppose, to make sure that the indices of how you define the Fibonacci sequence work out. So the convention that appears to be given in the question is that the first term has an index of 0, not 1. Okay. For which n does it have an integer solution? I am an expert on neither algebra nor anything to do with the Fibonacci sequence. So any integer solution. Maybe, okay, so if it has if it does have one integer solution, at least one integer solution, then we could factor that term out. And what would be left? Do we know anything about what would be left? So the last time I did a problem that had anything to do with the Fibonacci numbers, I was reminded in a comment that the Fibonacci numbers do have a closed form expression in terms of the golden ratio. I don't know if that'll help here. Okay, what I'm going to try is I'm going to assume that there is an integer solution, and we'll write Pn as a product of an n-1 degree polynomial and a monomial of that solution, and see if there's anything we can figure out. Just a stupid update. The convention of the indexing is in fact starting at 1, right? When n is equal to 2, I should get a 2 here, and that's clearly, this is the first term, second term, third term. So yeah, whatever. Doesn't really matter. I'm not really focused on the indexing and what I'm doing at the moment, but for those following at home. So it should have been clear from the beginning of the question, but any root of this polynomial, any real root, will have to be negative because as a function of x, it's increasing, and p of 0 is equal to 1. So we're looking for a negative integer solution, if any. So I've messed around with a few things here. I'm not really sure exactly what to make of it all. I tried, assuming that we have an integer solution, factoring things like this and then writing out all the relations that the coefficients of this factored polynomial have to satisfy in terms of the root of the original polynomial. And you just get a system of equations which look pretty straightforward. I don't know if there's anything we can say about them, but I noticed, if we go down, if I multiply this one on both sides by z, then I'll get an a0 times z, which we know is -1, and we can sub that in, and then we get a new equation. We basically get a relationship between the product a1z squared and a lower power of z. And if you just keep doing this, there's a general relationship that ak times z to the k plus 1 has to be equal to negative pk of z. That didn't really end up getting us anywhere. So what I tried next is using the definition of the Fibonacci sequence and splitting up the original polynomial into some other terms, basically writing it as a lower degree. I'll call these things Fibonacci polynomials, right? So we have a lower degree Fibonacci polynomial times x plus an even lower degree by 2 Fibonacci polynomial times x squared plus 1 is equal to 0. I don't know if this gives us anything in terms of trying to figure out when there's an integer solution. Yeah, I'm not sure. And then I just started computing manually in the first few polynomials, which of them could possibly have an integer solution. So again, any integer solution, any solution at all, any real solution has to be negative. The first polynomial clearly has a solution, which is -1. The second one is quadratic. We can solve it using the quadratic formula, but it turns out that the solutions will be complex. And then I looked at the third degree polynomial. As I said earlier, all of these polynomials, when you evaluate them at 0, you get 1. And then when I evaluate at -1, like basically the first possible integer solution you get, we get a sign change immediately. So as we take one step to the left of the origin, the sign changes of this function. And then what I did is I computed a derivative of this thing, and I show that that is also not 0 at any real value of x. And so the fact that as you move to the left, you go from 1 down to -1, you're never going to come back to 0. It's crossed over 0, it'll never come back to 0, so there's no roots to the left of -1, meaning that there are no integer roots of this polynomial of P3. I went on to P4, and I didn't prove this or anything, but I substituted in the first couple candidates for a solution, and as soon as you get to -2, this thing gets extremely large, and I don't possibly see how it could come back around down to 0. And I suspect the same thing would happen with P5. I've plugged in -1. I plug -1 into P5, I get a negative number. But, if I plug in -2 here, isn't this first term evaluated at -2 going to, well, let's try it. Let's just see what happens. This term looks a lot larger than this one in magnitude. This is a lot larger than that in magnitude. So I don't see how, I don't think there could be, for P5, I don't think there could be an integer root. I mean, I'm inclined to say now that the only answer is when n is equal to 1. Right? If I look at Pn of x, so Pn of 0 is equal to f0, which is equal to 1. Pn of negative 1, well, this depends on whether n is even or odd, right? If n is odd, yeah, so we get negative 1. Oh, of course, we just get negative 1 to the n of fn plus 1 plus negative 1 to the n minus 1 of fn. I'll write one more term at the top here, n minus 2, fn minus 1, down to f2. I'll write negative 1 squared here, even though we know that's equal to 1, plus f1, minus. Okay, so we get this. Can this ever be 0? Like this, if n is even, this is always positive. Right? This is simply the difference between the two, and fn plus 1 is bigger than fn. So this is always positive. And every pair of these things we get, those are always going to be positive, right? So let me make sure for an even value of n, what's p2 of negative 1? Is equal to 2 minus 1 plus 1, yeah, which is equal to 2. And p4 of negative 1 was equal to 4. So for even values of n, p of negative 1 is positive, and p of negative 2 is going to be even larger and positive. And it's just going to keep growing as we get more and more negative with the input. So I think Pn has no integer solutions. For even n. I think I'd have to, retrace my steps here and go through that in more detail again, but I mean, based on what I've said, I don't know if I've made a silly mistake, but okay, that's sort of my first thing. Okay, so let's try now when n is odd. When n is odd, this is negative. Each pair of these things is negative, right? If I group those together, n is odd, that's negative, that's positive. This outweighs that. Okay, so we certainly get a negative number in those two things. Well, these always just cancel, right? And I'm grouping those, right? Yeah, so odd, then even. Yeah, so let me check. Let me make sure that so P3 of negative 1 was negative. P5 of negative 1 is negative. And again, this if you pair these things together, evaluated at -1, they're all negative. If you evaluate at -2, they become more negative, and so on. So this tells me that Pn has no integer solutions for odd n except n equal 1. I'm not 100% confident here, but it just seems so certainly any root of this polynomial has to be negative. If we substitute -1, I just think this, by grouping each term in the polynomial as a pair, yeah, all these things, all these pairs are negative. I know that when n is even, we don't have a perfect pairing. There's like one term left over at the end. But that can't possibly, this term is equal to 1. And each of these differences, oh wait, no, when n is even, all of these things are positive. All of these pairs are positive. These pairs of terms. And when n is odd, they do group up in they do pairwise group up without any leftovers, and each of the pairings is negative. Again, evaluated when we evaluate at -1. And this positivity and negativity of the sums of the pairs only becomes more extreme as we start plugging in larger negative integers. I think this is the answer. I think it only has a solution when n is equal to 1. That's where I think I'm going to end this. Again, I would want to go through this again in more detail, but if I end up with, if I have some additional comments, or if I end up figuring out what my mistake is, if there is one, check the description. If someone has a different solution, or if I'm flat out wrong, let me know in the comments, because I'd be interested to know where my argument goes wrong on this one. Thanks for watching.